Congratulations, now you're ready to solve the exercises of chapter 4. And we start with exercise 4.1, which is a very simple exercise with a very simple utility function. I've depicted it here. You recognize this as a standard Cobb-Douglas utility function, and you are asked to compute the optimal consumption bundle, so the equilibrium consumption bundle. In fact, you could do this with your first year tools, equating the marginal rate of substitution to the price ratio. But given that we're now in intermediate micro, we will do the more advanced, the more general solution method by setting up the Lagrangian. And by doing so with a very simple utility function, this exercise is also very instructive in showing you the basics on how to do that. So enters Paul, who only likes Twinkies and soda, denoted by T and S, and who receives a budget of $1 from his mother. The price of Twinkies is 10 per Twinkie, and the sodas cost 25 cents each. And given this utility function, the optimization problem that Paul needs to solve is the following. So the Lagrangian function is the curly L. The thing we want to optimize is the utility, and we have to satisfy one constraint, which is within parentheses behind a lambda, and the constraint is that we cannot spend more than our budget, and we also don't want to spend less. So our budget is $1, and we can spend it on Twinkies, and we can spend it on soda. So the first order conditions of this Lagrangian are given by taking the partial derivative of the Lagrangian with respect to t, which gives square root s over t minus 0.1 lambda is equal to 0. The second condition is the partial with respect to s is square root t over s minus 0.25 lambda should in equilibrium also be identical to 0. And the third condition just returns the budget constraint. We take the partial of the Lagrangian with respect to lambda, and we arrive at 1 minus 0.1 t minus 0.25 s should in equilibrium be equal to 0. So we have a system of three equations with three unknowns, t, s, and lambda, and we need to solve for t, s, and lambda. And the best way to do this here is to try to get rid of one of the parameters in order to solve for the others. So first thing that you can do is in the first and second equation, you can bring the part with the lambda to the right-hand side of the equation, and then divide the second equation by the first. So sloppy notation, dividing the second equation by the first gives you that dividing square root t over s by square root s over t gives you t over s, and dividing 0.25 lambda over 0.10 lambda, and the lambdas cancel out, so that was the objective, and 0.25 divided by 0.10 is equal to 2.5. So we know that in equilibrium, Paul at these prices will consume 2.5 as many Twinkies as he will consume soda. Now we can then insert this into the third equation, the budget constraint, which is not unlike what you used to do before with the marginal rate of substitution. So in fact, this is identical to equating the marginal rate of substitution with the price ratio. So Inserting that in the third equation gives us that we spent our $1 on Twinkies, and we know that the number of Twinkies that we consume in equilibrium is 2.5 times the number of sodas that we consume, and we spend our money on sodas. So now we have an equation with only one unknown. So we can simplify the right-hand side to 0.5 S, and from that it follows that in equilibrium we will consume 2 sodas. Now, then we consume 2.5 times that number of Twinkies. So 2.5 times 2 is that in equilibrium we will consume, or Paul will consume, 5 Twinkies. And by doing so, he will receive a utility equal to the square root of 5 times 2. So his utility will be the square root of 10. And that is question A. Then we continue with question B. The school apparently found out that consuming Twinkies is very bad for one's health, and they increased the price of Twinkies to 40 cents. So the question is, how much will Paul's mother have to increase the lunch allowance to provide him with the same level of utility that he receives in part A? And we know that in part A, the utility that he receives was the square root of 10. Well, in the new situation, we have a new price ratio. So again, doing the T over S equaling the price ratio. In the new situation, the price of soda is still 0.25. The price of Twinkies is 0.40. So in the new situation, the equilibrium consumption of Twinkies will be no longer 2.5 times the number of sodas. Twinkies have become much more expensive, but only 5/8 times the number of sodas. Now, the question is by how much Paul's mother has to increase his lunch allowance. So, in order for Paul still to attain a utility level of square root 10. Now, his utility level is 5/8 times the number of sodas, because that's the number of Twinkies that he will consume in equilibrium, times the number and the number of sodas. So we have the following expression for his utility function as a function of the equilibrium number of sodas, and that is the square root over 5/8 S squared. And the condition is that Paul needs to be just as well off as before, so his utility needs to reach the level square root 10, which then implies that S squared should be equal to 8/5 times 10. So that should be equal to 16. So the equilibrium quantity of soda consumed is equal to 4. And in the new situation, the equilibrium number of Twinkies is 5/8 times the number of sodas, which is equal to 4. So it's equal to 2.5. Now, what does it mean for the amount of money that Paul needs to have? Well, in the new situation, the price of soda times the new amount of sodas consumed in equilibrium plus the price of Twinkies and the new number of Twinkies consumed is the price of soda remains at 0.25. Paul will consume 4 sodas. The price of Twinkies is 0.14. Paul will consume 2.5. So he needs a budget of $2 in order to attain a utility level of square root of 10 in the new situation. So he needs $1 more than in the original situation. So given that this question asks for the extra income needed in order to reach a given utility level, another way to solve this is by using the expenditure function. And I think it's instructive to show you that solution method as well. So let's do that. And again, our starting point is in equilibrium, the ratio in which we consume soda and Twinkies is identical to the price ratio between the two. Or we could also rewrite this as S is PT over PS times the number of Twinkies. And let's denote that equation by a star, because I will refer to it. And this is a very general approach. And we also have the budget constraint. So our income needs to be spent on Twinkies and on soda. So that gives us the second expression. And now we insert the first one into the second. So we replace the S over here by this expression that we have over here. So this one. So if we do that, we get that income is equal to 2 times PT times the number of Twinkies. So we have an expression in Twinkies only, or alternatively, the number of Twinkies that we consume in equilibrium is a function of our income and the price of Twinkies. So it's a Cobb-Douglas function, so it doesn't depend on the price of soda. And following the first equation, so the one that is given here within the green circle, we know that in equilibrium, the number of soda that we consume as a function of income in the prices is income divided by 2 times the price of soda. And these are the compensated demand functions for good S and T. So it's the equilibrium consumption of soda and Twinkies as a function of income and prices. And we substitute this into the utility function in order to get the indirect utility. So we have the direct utility function. So direct utility function is expressed in the number of units, which gives us the direct consumption utility. But now we replace the T and the S over here by these two expressions, such that we get the indirect utility function, V, which is a function of income and the price of soda and the price of Twinkies. Now, these prices and income do not give us direct utility, but they allow us to buy a certain amount of Twinkies and soda, which do give us consumption utility. So this is why it's called an indirect utility function. Now, replacing the T and the S in the direct utility function gives us square root I over 2 times PT times I over 2 times PS is identical to y over 2 times 1 over the square root of PT times PS. So this is all under the square root term. Now we're pretty close to the expenditure function, which is the objective. We want to get an expression for the expenditure function, because if we solve this expression for income I, then we have an expression for the expenditure function, because the expenditure function E is the inverse of the indirect utility function. So it's identical to 2 times the square root PT PS times U bar. Now, how do I get at that? In fact, what I do is I take this expression that we have over here, and I say, okay, let's fix the utility level at a certain value U bar. So we replace this one with U bar, and then we solve for I. So, and then we get bringing the things in denominator to the left-hand side, we get that y is equal to 2 times square root PT PS times the fixed utility level bar U. And then we can simply replace income by expenditure, and we have our expenditure function. So the expenditure function gives us the amount of money that we need, given the prices PS and PT, in order to attain a consumption utility level of U bar. Now we know that in the original situation, our utility level was square root of 10. But now we face new prices, and we can now easily find the minimum expenditures that we need to make in order to attain a utility level of square root 10, given the new prices, by just plugging in these prices. So the expenditures at a price of Twinkies of 0.4, the price of soda of 0.25, and the fact that we want to reach a utility level of square root 10 is equal to simply inserting the prices and the utility level into the expression of the expenditure function. So it's 2 times the square root 0.4 times 0.25 times the square root of 10. And you will notice that this one is equal to 2. So we need to make an expenditures equal to 2, which is 1 more than the $1 that we had before. So our change in expenditures is identical to 1. So that gives us the solution to this exercise, but using the expenditure function. And I hope that this shows you how all things are related.